So in today's lecture, I think this is one of the most important lecture for this course, in my opinion, because this is a part that allows you to understand why we have a design equation looking like a certain form. Okay, without letting you know the reasoning, it's just an equation. But after today's lecture, if you understand what happened, in the future, you not only use the equation, but also you can understand why this equation is meaningful. Okay, so in the future, when you are making your own mechanical design, at least the concept right here could be helpful. Okay. So this is just a review of what we have done last time. This is the maximum shear stress model, and let me remind you, this is for the most conservative model. So the design region actually is gonna be the smallest, because we're conservative. We don't want to design, we don't want to have a large design space. We want to have a smaller one. So this is actually the smallest, most conservative. Later on, the next model, when we, after the introduction, you will realize the next model is gonna give us a larger design space, which is less conservative with higher risk, but you have a larger space. Okay? Now, so the first model is so-called the MaxStrain energy model. It came from many similar equations that you have seen in the past, but not so quite familiar. I'm going to go through everything step by step. First, you need to understand what's this guy. So it's a box. It's like a small element inside your material. And let's recall how we solve a shaft problem. We have force balance, moment balance, and then we study the shear force, we study the bending moment, torsion, and then we pick up a point inside the shaft. We claim that the point that is carrying the most load. So that tiny piece, a small cube, is just like a cube right here. So it's a tiny dot inside the material. And this could be the small piece that you are investigating in your mechanical part. Now, in general, this part along this coordinate system, it could be carrying forces from different directions. From here you can tell there is no shear force, so you can say it's a kind of analysis along the principal stress coordinate. So assuming you are able to find out what's the principal coordinate system, and on that principal coordinate, there's only normal force. There's no shearing forces anywhere. Now, after this, these forces pulling along 3 different directions, this box will be expanding. And there is a dashed box illustrating the deformation of this tiny piece. So let's take a look at the original size of this tiny box. It's having the width of dx, dy, and dz. So that's the original size, already a very tiny box. After you pull away along 3 different directions, we have super small deformation along each direction. So delta x, delta y, and delta z. From here you can tell delta d is already small, delta is even smaller. Okay? Now, the first thing we're going to derive is from the definition of stress. So along each direction, we basically can realize the relationship of the principal stress and the pulling force. Basically, stress equals to force over the stress area. Since they are boxes, so the area could be calculated quite easily. Take the first one as an example. The size of this box right here basically is dy times, this is dz. So the first equation, if you use this fx divided by dy dz, basically you get the principal stress along this particular direction. So similarly, you have the second one and the third one. That's quite simple. Now, let's go to the definition of strain. Strain basically is a ratio of the deformation over its original length. So by definition, if you understand what's going on right here, all the deltas are the deformations along each direction. All the d's are its original length. So I can easily compute the strain along each direction. The first one basically is delta x over dx. That gives you the strain along the x direction. Similarly, you have the second and the third equation. Now, here comes the Hooke's law. Hooke's law describes the linear relationship between the stress and the strain. However, it covers the information along the direction that is not on the stress direction you are investigating. For example, if you are pulling the material up and down, you should be having deformation along this up and down direction. But since you could be pulling left and right, so when you pull up and down, your material shrink a little bit horizontally, but when you pull left and right, your material shrink a little bit up and down. So the stresses along the other two directions will be affecting how much deformation you have along the first direction. And Hooke's law describes how much effect that came from the other two stress directions. So if you don't have effects on the other two directions, basically stress equals to Young's modulus times your strain. But if you do have stress along the other direction, then you need to minus the stress along the other direction, multiplying the Poisson's ratio. Also, similarly, do the same thing for the z direction. So that's what Hooke's law is about. And what is Poisson ratio? Poisson ratio is a ratio of how much shrinkage you have left to right when you pull up and down. It's a ratio. Okay? So there's something called negative Poisson ratio material. If you have a material, when you pull up and down, it actually expands horizontally, then the Poisson ratio is negative. Because usually if you pull something up and down, it shrinks horizontally. It shrinks left and right. Now, that's a usual material behavior. So we treat this kind of shrinkage horizontally as positive Poisson ratio. Okay? Now, similar to the first equation for the Hooke's law, you can have the second and the third equation. It's basically the same equation. Now, we have definitions of stress, definition of strain, and we put stress and strain together by Hooke's law. Now we want to study the strain energy. So strain energy is like how much energy you store in the material when you are stretching a spring, like a spring energy. So assuming there is no loss of energy, if you pull a string and when you release it, it returns back to its original shape. If you didn't pass through its linear elastic material region. So suppose there is no energy loss. So similarly, right here we are assuming whatever force we are applying, we are keeping the amount of the force within certain range, so our material remains elastic. So we're staying in the elastic region. The linear relationship between the stress and strain is still there. Okay? So later on we will talk about greater and greater stresses, greater and greater forces until we reach yielding. That's the extreme limit that we can reach. We cannot go further. Because if we go further than the yielding point, then the material yields. It doesn't return back to its own shape, original shape. Now, let's talk about how you can compute strain energy. So if you remember, for a spring, the amount of force that you apply is linear proportional to its increment of length. So there is a linear relationship like this. And usually we will say the slope is k. So you can say F equals to k times delta x. If you want to study how much energy that you store, basically it's like how much work you apply. And when we try to compute work, we usually have force multiplying how much movement, how much displacement that we perform. But since the force is depending on, I should say, force and the displacement, they are dependent. So the more force you apply, the more displacement you get. So then they are following this linear relationship. So the energy that you apply or the strain energy you store is not exactly F times the displacement. It's actually for example, you stop right here, is actually the area right here. So you can easily tell the strain energy is a half of F times delta x. Okay, so that's how much work you apply, and assuming those work were stored as strain energy. That's why we have all these right here. Along the x direction, we assume the strain energy that we store equals to a half of the force times how much displacement you have. So this is the strain energy that you store inside the material along the x direction. Similarly, you have the y1 and the z1. Okay? So in total, basically, you sum them up. This is a total strain energy that you store inside the material. Now, all we need to do right now is to substitute some of the equations that we derived earlier into this new equation. So the way we are trying to do it is to eliminate F and delta, replace them by stress and strain. So and you realize you can easily do it by just replacing terms. Fx is gonna be Sx times dy dz. So you do have a Sx times dy and dz right here. These three terms. Now your strain, your delta equals to your strain times dx. So delta equals to strain times dx. So overall, you always have a dx dy dz right inside the bracket. So you can take them out. And inside the bracket, you realize you do have Sx, sigma, epsilon x plus sy, epsilon y plus sz, epsilon z. So what we are going to do next is to plug in the Hooke's law into the following equation. So at the end, you will get a longer equation like this. However, you eliminate all the strains. Everything left are just stresses, the principal stresses. And of course, we introduce one more term into the equation, which is the Poisson's ratio. Okay, you can try it by yourself, and then this is what you will get at the end. You do have a Young's modulus right here. Okay? Everyone okay right here? It's just wrong. Okay, but it's nothing too difficult. It's just a long equation. So what do we do next? We will study, because you know whatever material you pick could be having a different size. So we want to have a more general equation. So we would like to study the strain energy per unit volume. So no matter what exact size you pick for your box, this value should be the same. This equation should be general enough. So we derive this unit equation. Basically, it's the strain energy per unit volume. And what's the volume of the box? It's basically dx, dy, and dz. So small u represent the energy per unit volume. And that actually simplifies the equation we have, because we get rid of dx, dy, and dz. So we will get some equation over there on the right-hand side, and we cannot do anything further. That's the simplest equation that we get at the end. So what's next? So the following step, I think, is very important. It's a very fundamental concept for many design equations. So again, we go back to tensile test. Let's think about a tensile test. So a tensile test is basically it's like this. You are pulling a material with a principal stress along one direction. There's no stresses along other directions. And if you draw the Moore circle, like I said in the past, it's like this. Okay, the Moore circle is gonna be like a circle that lies on the stress coordinate and tangent passing through the origin of the stress, shear stress diagram. So what's the elastic strain energy per unit volume for tensile test? So basically it's the same equation. This is a general equation for all loading conditions. But let's talk about a special case where we are dealing with the tensile test. And we know in tensile test, we only have principal stress along x direction. There's no other principal stresses. So basically, all the sy and sz become 0. That's why we can quickly get what would be the elastic strain energy per unit volume for the case of tensile test. That's the equation. That's how we get it. Okay? Now, for tensile test, we know this is the strain energy per unit volume. We want to know what would be the limit for this value? So just like what we did for maximum shear stress model, we think about the design limit. So the limit happens when you enlarge your stress until this stress is as large as your yielding strength. So Sy or Yp, sometimes people use Yp. Yp is like a yielding point, okay? Or just Y for sure. Sometimes people just say Sy, okay? Ys, because we are on the coordinate of principal stress. And of course, it's the same as some people use sigma y. Okay, they are the same thing, same number. Now, when this principal stress is as large as your yielding strength, you cannot expand further. You cannot apply a greater stress. That's the limit. That's the extreme. So we know for tensile test, the allowable limit is this quantity, this value. You just replace your Sy by Sx by Sy. So that will be the limit. And we already know that's the limit. It's like a material property. That's a property for any material or metal. That's the upper limit of strain energy per unit volume. So even when we go back to the general equation, we know this should be the limit. Because it's like we use tensile test to realize it. So we use the concept to realize what's the upper limit of this value. So even when we change how we apply stresses, we can have principal stresses everywhere, we still believe this is the upper limit. You cannot find a different concept and explain why this value could be greater. Okay, because tensile test is the one way to deform your material with the simplest loading condition. And that test applies the most the easiest way to understand what's the upper limit. Okay, and suppose that's the upper limit for that material, and it's a value. Basically, it's a number. So even if you try different tests, supposedly that number should be the same. Okay. Now, if we believe this is right, then we can say this general equation should be smaller than or equals to this upper limit. That's how we get this design equation. Okay. So sometimes students may forget how we got here. So you just, okay, that's the design equation. Forget about what happened earlier. But I actually don't want you to memorize the equation. You can always find it in the book or from the internet, from the literature. But the concept, I feel like it's more important, how we get here. Okay, so once you have this general equation, basically the idea is the elastic strain energy per unit volume for any general loading condition must be smaller than or equals to the upper limit we found here. And in this equation, we realize we can get rid of 2e from both sides. And we can take a square root. So on the right-hand side, we have SYP only. Okay. Now, any questions? Is it difficult to understand? Again, you don't need to memorize it. If I need you to use it in an exam, I will give you the equation. All I care about is whether you understand what happened. Okay, seems like you guys are okay. Now, let's try to make a drawing of it. So for the design, for the diagram for plane stress, we draw the design limit by the dashed line. That's for the maximum strain energy, maximum shear stress model. And I introduced a second model, which is the maximum strain energy model. It looked like the equation I showed you earlier. And if you want to make a drawing of it, it's not so easy. So I did something right here in this particular slide to help you understand how to make a drawing of it. Where did this come from? Basically the same equation that we had earlier in the previous slide. What happened was, because we are only talking about a plane stress or plane strains problem, there is no stress on the third direction. So Sz equals to 0. And I just convert x and y to a and b. Like I said earlier, a and b doesn't need to be principal stresses along any direction. Basically, they are the two principal stresses on the plane. It doesn't matter which one is the bigger one, okay? And that's how we derived the 6 equations for maximum shear stress. So we did the same thing for this time. I just named the first one as SA, name the second one as SB. It won't be any different if I swap the definition of SA and SB. Same drawing right there, because it's gonna be symmetric. So an easier way to make this drawing is to have a rotation of the coordinate. Since I know this drawing is gonna be symmetric along a coordinate that has a 45-degree difference with the original coordinate, so I made a rotation of the coordinate by 45 degrees. So I define a different coordinate that is SA prime and SB prime. SA prime and SB prime is the coordinate that has a 45 degree rotated from the original coordinate. By doing so, I can derive how SA and SA prime and SB prime are related. So all I did was just plugging in. So from here, I plug into the equation above and did some math. At the end, I realized along the SA prime, SB prime coordinate, it's an equation of an ellipse. So it's gonna be an ellipse along this SA prime and SB prime coordinate. And if you try to plug in some values, and then you will realize it's gonna pass through these 4 corner points, okay? And it's gonna be slightly greater than the 6 dashed lines that we had for maximum shear stress model. It's gonna be a little bit larger. And especially for the very left edge and the very right edge, you realize you can have more aggressive design at the edge. So this new model allows you to have more dangerous design decision toward the boundary. It basically gives you a greater design region. So how come we can have a greater design when we choose a different model like this? I think it all came from the concept of Hooke's law. Because think about it, when we have a material that is carrying some stress, it's a value, and we understand what's the limit of that value by yield strength. So usually we only study the stress along principal coordinate. We don't even care about what happened along different directions. That's why for maximum shear stress model, we know the maximum shear stress for the Morse circle is like a half of your normal stress. If you have, here's your maximum shear, right? If you have a Morse circle for the tensile test, you know from the maximum shear stress model, basically it's a number linearly proportional to the stress you apply. We just claim how much this value should be constrained by the upper limit. So usually we will say, okay, it's gonna be like this. That's how we have a design equation for maximum shear stress model. When we deal with this equation, we never talk about what happened along different directions. However, in maximum strain energy model, we introduce one more concept, which is Hooke's law. In Hooke's law, when we pull the material along up and down direction, we care about how the stresses along different directions affect the deformation. So when we pull up, reaching to some limit, and when we pull left and right, it actually shrinks the up and right direction a little bit. So it seems like it allows you to pull up and down a little bit more. Okay, so that Hooke's law allows you to do a little bit more. So over here you can take a look at the distance from the origin to the very edge. If you have some material that has 0 Poisson ratio, then this becomes, no, it's not impossible to be 0. If you have, I should say, 0.5. If you have a material that has 0.5 Poisson ratio, what does that mean, 0.5? That means if you have a material like this, and if you are pulling up and down, for example, stress right here, and supposedly it's gonna shrink, right? It's gonna shrink. So Poisson's ratio, the ideal extreme of Poisson ratio is 0.5. Why is it 0.5? Because it's like you can shrink up to a half of it. The amount of your shrinkage can only be a half of the original length. Okay? If this is the original length, you can only shrink up to a half of it. You can never shrink greater than a half. So if you have a Poisson ratio of 0.4, that means you have some material that allows you to shrink up to like 40% from each side. It's like this. This is like 40% of the entire material. Okay? So in real world situation, Poisson ratio can never reach 0.5. It usually is a number smaller than 0.5. But usually it's not 0. If there's a material that has 0 Poisson's ratio, that means you can pull and it doesn't shrink. It would be weird. If you have a material that you can do this, and when you lengthen it, the width remains the same. That means Poisson ratio is 0. That kind of material doesn't exist. If you can do that, that means you can keep on pouring, and then you have more and more material, right? So usually Poisson ratio is a number within 0 and 0.5. 0.5 is like the theoretical extreme value for Poisson's ratio. And if you try that number here, then you have a square root of 0.5. And basically it's like a half of it, right? And that means this length is gonna be square root of 2 times the yielding strength. So that means when you have Poisson ratio of 0.5, this position is gonna overlapping with this upper right corner. So only if you have ideal 0.5 Poisson ratio material, then you will have this ellipse model passing through this corner point. So that will become the smallest elliptical design shape that you can have under the concept of maximum strain energy. However, that never happened, because in real world, Poisson ratio is smaller than 0.5. It's usually a number within 0 and 0.5. So, from maximum strain energy model, this red ellipse is typically, usually, or always wider than the dash boundary from maximum shear stress model. So this maximum strain energy model is less conservative because you have a greater design space. You allow your design to have a greater freedom to be to carry loads. Okay, you allow loading condition, for example, right here. For maximum shear stress model, it doesn't allow loading condition over here because for that model, a design under a loading condition here is violating the yielding constraint, yielding criteria. But in a different concept right here, it allows you to have a design right here. Okay, so that's the difference between two models. Which one is right? None of them is right. Because in real world, they're just math. They're design concept. And you can never have a material that is so pure, so isotropic. It's perfectly the same everywhere. None of the material is perfectly the same. Nothing is perfect. If you check the literature and get a value of Young's modulus, it's only average value of 1,000,000 tests. So the real Young's modulus of a material varies within a range. And even for a piece of the metal, the Young's modulus everywhere would be different, because you can hardly have isotropic material. So what do we deal with it? In the real world, there are so many uncertainty. Those are uncertain numbers. So we need to apply safety factor. We allow those noises to be eliminated or to be those issues to be avoided by the trick of safety factor. So we don't push ourselves to the very limit, because your material could fail. Okay? So from now on, when you work really hard, you don't work to the extreme so you could die, right? You still give yourself a slight safety factor so you survive. Okay, so you still push hard, but you apply safety factor to yourself. You don't want to die. Anyway, if you apply safety factor to the maximum strain energy model, the way we do it is to keep the yielding strength on the right-hand side of the equation and put this safety factor underneath the yielding strength, just like what we did for the maximum shear stress model. That is one of the reasons why we would like to take a square root, because we want to keep the right-hand side looking like the same form, okay? So, when we do that, it's just like you are pushing this elliptical limit from the yielding point to somewhere inside. How much further inside? Basically, divide Sy by a positive value n, and also greater than 1. So if n equals to 2, you push this yielding point to a half of it. Then you will have a design shape so small like this. If you have a 10, if your safety factor is 10, it's like you shrink this limit 10 times, you have such a small design space. Okay, so it really depends on how safe you want to have for your design. Okay, and since we can choose our safety factor, then we don't need to worry about whether a material could have standard deviation. So let me tell you a little bit more about statistics. So if one day you have a design and this is your stress, and here is your yielding strength, and let's say you have a design, for example, here is the stress you're going to apply to your material. So if your design is right here, then you satisfy how much, you satisfy the design equation where your stress is smaller than your yield strength, right? But your workpiece could be carrying different loads. This value could be sometimes larger. So if you enlarge the stress and reach a different position, so for example, you are carrying a different load, and now the material is having a greater stress. Even though in this situation you still satisfy the design equation, there is a greater risk. Why is that? Because you know you have the way you compute stress is based on how much moment you have, the dimension you have, and some geometrical information here. How can you be so sure the moment you apply is exactly like how you estimate it? And how can you be so sure the dimension right here is exactly right, the dimension here is exactly right? When you design a shaft, and if you are looking for diameter of 10, it could be 10 plus and minus, there's a slight difference. Or it could be greater. It could be greater tolerance, right? So that slight difference makes the stress greater or smaller. So in fact, if you have 10,000 pieces of your part and they are carrying the same load, statistically, it looks like a distribution like this. Okay? And when this distribution is far away from the upper limit, the probability of failure is low. Sometimes you don't need to care about it. However, when you are carrying a greater load, this uncertain distribution could have slight area that is violating the upper limit. So this is where this is called a probability. probability of failure. Okay, so if the distribution right here overall is 100%, there could be a slight percentage where your stress is greater than the upper limit. So this could be probably 2%. Let's say this is just one example. Maybe this is just 2% out of your overall distribution. If you do face this kind of situation, that means when you have 1,000 pieces, 20% of the pieces will fail. If this is drawn precisely. Okay, so design of mechanical component cares about failure rate, reliability. That's why they don't want this mean value to be too close to the design limit. They want to keep a gap. Otherwise, if you have, for example, this is your upper limit. If you have your design that is so close to the upper limit, and if you truly make 1,000 pieces and do statistical analysis, you could have a great area, for example, 30% right here. You could have 30% of your piece that is violating your design equation. So you really don't want your design that is too close to your upper limit. And that is why they want their design not exactly by the upper limit only. They want to divide this value by a safety factor. So they want to limit your design within a range so it's far away from the yielding strength. So there could be an upper limit right here. So this value equals to your yield strength divided by n. So your design can only be as big as this. So your distribution will be something like this. In that case, you can control how much failure you have. So this probably would be as low as, for example, 3%. Maybe 3% is allowable for your company. Okay, so nowadays, this is so-called system reliability or reliable design. They work on something like this so precisely. They know how much parts will fail. Like your cell phone. How come your cell phone has an exact amount of warranty? They guarantee your cell phone won't break within 2 years. How do they know? Because they have done this so precisely. They know some part in your cell phone will start to break 2 years later. Okay? And later on when we talk about fatigue, you will realize the material strength gradually reduce when you apply dynamic loads. So nowadays, engineering are so precise, they know when the part will lose its strength to a certain limit, certain value, and it could break easily several years later. Why do they do that? Why do they want your part to break somewhere in the future? They want you to buy a new one. Okay, so in old days, for example, when I was young, usually all the parts are hardly broken. They are so strong because at the time, 20 years ago, 30 years ago, the engineering was not so advanced. Sometimes they over-design. They put more money and material in your part, so your part becomes so strong, it doesn't break. And companies realize they don't want to make something that is too strong, because their product doesn't fail. If their product doesn't fail, you don't buy a new one. So those evil companies, they design their parts precisely within certain performance level or strength level. Enough is enough. Over is not good for them because doing better for you make them lose money. They want to do it precisely that you're satisfied, you're willing to pay for this particular one, and they sign a contract with you and let you know how many times later you will break. When you sign and pay, you agree that will happen, and when you fail, you buy a new one. So nowadays, engineering are so precise. Now, what's next? Okay, here's a comparison. Tomorrow I will give you some homework, basically some stress analysis problem like this, and we will use different models to compare the difference between them, and you will realize this part of the homework become easier because all you need to do is to apply numbers into those equations. So actually the course is getting easier, I think. The first exam, I will say, is the most difficult one. Okay, let's try to study this particular plane stress problem. Right here, we have a diagram representing its stresses from different directions. If you draw the Moore circle, you realize on the right-hand side, it gives you positive 40 megapascal of normal stress. So here's 40, and you have clockwise 30 megapascal shear stress. In my coordinate, I say counterclockwise is positive, then my clockwise shear stress is gonna be negative. Okay, so negative 30 right here, rotate by 90 degrees here, that will be rotating 180 degrees in the Moore circle coordinate. So at the end, I will have a compression 20 megapascal. Compression for me is negative, so negative 20 here. Over here, the shear is counterclockwise, so it's positive. That's why negative 20 and 30. So 30, positive 30. So I have 2 points that forms my Moore circle. And first what I did was I tried to compute the radius. That's how you can compute the radius. And then first and second principal stresses could be determined by finding the center point plus the radius or minus the radius. So go back and review those. You should be able to compute for the maximum shear, first and second principal stresses. Now, let's say this material has a yield strength of 100 megapascal and the Poisson's ratio is 0.3. What's going to happen is, for maximum shear stress model, you basically have this equation. Your maximum shear should be smaller than or equals to your yield strength over 2 times your safety factor. So just plug in all the numbers. Maximum shear has been calculated. The yield strength has been given. Plug in. Then you found a number n should be smaller than or equals to 1.18. What does that mean? That means under this low condition, with the material you use, you have a maximum safety level of 1.18. That's the most safety level you can get. Your safety level can only be lower than that. That's the maximum safety level you reach. Okay? So that's what that equation means. Now we know this analysis came from a most conservative analysis, that is a maximum stress model, maximum shear stress model. That's the most conservative one. And this model should give me a lower safety factor. That means it's warning you your safety level is low. We are conservative, your safety level is low. if I try a different model, it's less conservative, that different model could tell me something different. The estimation of my safety level could be higher because the concept of strain energy model is less conservative. So let's try it. Using the equation that we derived earlier, plugging all the numbers, first principle stress, second one, Poisson ratio here, and also the yield strain, plugging all the numbers, and truly compute what's the maximum safety level I can reach under the concept of strain energy model. At the end, we truly get a greater number, 1.44. So that means in a different concept, I actually have a greater safety because it's a less conservative model. So in fact, which one is real? Maybe in the real world, it's some number in between. Because, you know, like I said earlier, there's so many uncertainty everywhere. You just don't know how your uncertainty look like. So if you truly want to study the safety level, you need to do a lot of experiments. And then you realize how safe your design is. But in the real world, usually we don't try to figure out what would be the real safety number. So in companies, what they usually do is for example, they are designing a mechanical part truly carrying this kind of load and truly having a Young's modulus, material property of, yield strength 100, Poisson ratio 0.3 right there. That's what they truly do. So what they, in the usual case is that for the company, whenever we are designing this, we decide to have some safety level of 1.5. Let's say this is a company's decision. We want a design with a safety factor of 1.5. So when your safety factor is 1.5, and they probably mean, okay, 1.5 under which model? Okay, so if you are an engineer that has poor knowledge of mechanical design, you probably cannot make good use of those equations, then you could do something wrong. Because when they tell you safety factor, they need to say which model they're using, because it's different. So if they tell you, okay, let's design this with a safety factor of 1.5 using strain energy model, now they probably only allow you to change the geometry. So keeping the same load condition, keeping the same material, and there is something that you can change. That could be the. In this case, you cannot change, because once the stress is set, you have to change something here. But if they allow you to, we can plug in everything, like all the stresses. We can convert them into 32 m over pi d cube if it's a cylindrical geometry. Then we can truly decide how much bending moment that we carry and the dimension, how large your shaft is. So design equations allows you to decide which parameter to be tuned. So once a decision is made, some other values has to be adjusted accordingly, and you need to know which equation to use. Okay, so I hope in the future when you make mechanical design, you can make the right decision. Now, that's the final page of this particular slide. In this course, we do have a different model that's gonna be so-called the maximum distortion energy model. Let me just quickly show you what this is about, but it's gonna take some time for me to cover the whole derivation. So I may not be able to finish this model today, but I can slightly talk about it. Okay, so this was what we did earlier. We have a dashed line maximum shear stress model. We have this elliptical red boundary. It's from the maximum strain energy model. Now, to talk about this maximum distortion energy, it requires me to introduce a new concept right here, which I will talk about tomorrow, because it will be taking too much time right now. And there will be some stress analysis as well, and of course some assumptions. And at the end, the goal of maximum distortion energy model is to form an equation just like this. Okay? Let me tell you the conclusion. At the end, we have an equation like this. And similarly, we take a square root of both sides. And we call this guy von Mises stress. So remember in the pre-test, I asked everyone, have you ever heard of von Mises stress? This is von Mises stress. So what is a von Mises stress? It's a stress that can be computed by the principal stresses along all three directions. So von Mises stress is like an equivalent stress. So if you have some stress along x or y or z, your von Mises stress will be larger. But it's an overall stress behavior along all three directions. So von Mises stress has no direction. If you go to internet and Google, let me show you. If you Google ANSYS von Mises stress and you just pick up a picture. Okay, let's pick up this picture. So this is ANSYS is the software we're going to learn later on. And over here, after a certain setup of the mechanical part in the computer, set up the material, set up the boundary conditions, apply a so-called mesh, and run the simulation, you realize it can tell you something called von Mises stress. And you see, it tells you it's an equivalent type. And there's a unit right here. And there's a maximum value, there's a minimum value. So from this example, you realize it never tells you the direction of the stress. Remember when we, before today, whenever we have stress analysis, usually it comes with a vector, a direction. But von Mises stress is something that has no direction, because it's an equivalent stress. It's an overall behavior considering principal stresses along all three principal axes. Okay? So tomorrow, when we talk, after I introduce the so-called maximum distortion energy model, I will introduce how to compute von Mises stress. This is the general equation for von Mises stress. It's an equivalent stress. And why do people like to use this? Because you don't need to calculate the direction. So it's like, okay, someone punched me in the face from the front. At the same time, another guy attacked me from the side. So my head is carrying loads from one direction and the second one. Equivalently, my head is carrying some equivalent load based on the stress along this direction and this direction. So does my head care about where this stress comes from? My head only cares about how much, what's the level of the stresses my head is carrying. If it's over a certain limit, my head will explode. Okay? So in mechanical design, in software, sometimes we like to use this model because the stress analysis can be done in an equivalent way, so we don't even need to care about directions. However, as you can see, the derivation is quite long. So in tomorrow's lecture, I know it's 9 o'clock, where you may fall asleep even more easier. But in tomorrow's derivation, it's gonna be quite long and quite weird. To be honest, it's very weird. You may have never heard of it. So this PPT is already online. If you are interested, you can go back home and then quickly have a quick glance of tomorrow's slide. And tomorrow I will talk about it. And I believe if you review in advance, you can understand it more easily tomorrow. Okay? So at the end, maximum distortion energy model has no Poisson ratio. There's no Poisson ratio here. So at the end, the maximum distortion energy model is basically same equation treating the Poisson ratio as 0.5. If you want to have a good if you want to memorize it more easily. The difference between maximum distortion energy model and maximum strain energy model is just like treating your Poisson ratio as 0.5. Then you get maximum distortion energy model. But the concept doesn't come from treating the material as an ideal material. The derivation of maximum distortion energy model came from a new concept, so-called distortion energy, and studying how much distortion energy a material can take, then derive something like this. Then derive like the equation like this. Okay. So overall, at the end, if we apply safety factor, this is what we're looking for. Okay. The original models, the dashed line, the red curve, and the blue curve, and also the ones with consideration of safety factors. Okay, so in the future, when your boss tells you, okay, let's use a safety factor of 2, you need to ask him, okay, which model? Okay, if he cannot answer you, that means he doesn't understand mechanical design well enough. But don't say that to him. Say that in your mind. Okay, that's what I can cover today. So, you know, the timing is I still can continue, but I won't be able to finish this. How about we talk about the tests? Yeah, we can spend some time on how to solve the test that we did earlier. Tell me, do you have did you finish grading?
Finish.
You finished grading?
Yes.
Okay, you're such a good TA, thank you. Okay, maybe you can give back to them. What's the average? Do you know? Very bad?
Yes.我有把成绩放在那个名单上。
Okay. What's the total? 10? 10 points?
Yes, 10 more.
Okay. I saw someone. Okay. Okay. Do you want to do a makeup test?
Yes.
Okay. So don't worry about this, because you will be worried, right? Now I agree. I think we should do a makeup test, because it's not looking good. Not very good. Okay. We do have some good ones. Only a few. So for the makeup test, what I usually do is I try to help whoever didn't do well enough. And of course, it's a little unfair to the ones who did pretty well, because you become less competitive. But to be honest, don't worry. Whoever fall behind usually cannot come back. So I'm just trying to help the students at the middle. Trust me, there's always someone already fall behind. And whoever you are already in the top, don't worry if I try to help the ones in the middle, because if you are good, you are always in the front. So you can still get your scholarship. But I need to help more, so I don't need to make score adjustment at the end. Okay, so usually for the makeup, let's say the total of the test is like 10 points, and let's say you get 6, then you lost 4 points, right? So maybe the makeup is trying to cover how much you lose, how much you lost. So if you got a 2, then you lost 8, and the makeup is gonna, add something to what you lost. So if you got a 9, then you have very little room for improvement. Okay, so I will try to make everyone happy, but I know not every one of you will be happy, because whoever is in the front doesn't want makeup, whoever at the middle, well, anyway, I will announce how we do the makeup. Today, do you have my solution? Yeah, okay. Did you, I think I took a picture, right?
Yes.
On Facebook.
Oh.
Okay, I can show them the Facebook. Line message? Line? I'm going to Okay. I need to know my Facebook password. Okay, so yeah, we download this, and then open this by this one. Okay, how do I? Okay. Yeah, so first you need to do force balance. Okay. So once you have the force balance, what I did was I used the trick to have a shear diagram first. So at the left edge, there is a reaction force pushing up, and there is a uniform distributed load everywhere. Do you still remember the problem? Yeah, it's uniformly distributed everywhere. So the shear keeps going down because there's a distributed load pushing down everywhere until it reaches to somewhere here. I think that's where we have the second bearing. This is first bearing, second bearing, and there's where I have a second reaction force, and it pushes up to here. And then when you walk toward right, you will be experiencing the distributed load more until you reach a certain point right here, and that's where you have the force on the edge, and then it pushes you back to zero. Then the arrow represent the integral I took. So there was a first integral right here. At this equation, I took an integral here, and then I plug in some numbers to find the constant. Because there's no force on the left edge of the bearing, so the moment should be zero right here. However, on the very right edge, there's a force at the right edge, so there's moment. So it's common if you see some moment at the very right edge. And all you need to do is to plug in some numbers to get the equations and then make a drawing. So the bending moment diagram looks a little weird, but you can see right here, that's where you have the maximum bending moment. And you can use 32 m over pi t cubed to realize what would be the maximum normal stress. And it's a shaft with pure bending. There's no torsion. There's no torsion, right? So, and we don't have forces along different directions. So it's like it's purely bended. So at that worst case position, this material is being pulled from left to right. So it's just like tensile test. So the Mohr circle is so easy. It's like this. Okay. Let me download the problem. Here's the problem. So this force is bending the shaft, and its own weight is bending the shaft. The reaction forces is bending the shaft. There's no torsion. So if I study, this is the position where I have the largest bending moment, and if I pick up the top point, as you can see, it's being bended this way. So over here is applying a tensile force. But on the edge, this is the neutral plane. So there's no stress on the edge. There's no torsion. Okay? So over here, actually, no stress on the neutral plane. Okay? So when we talk about, maybe I should do side by side. When we are trying to make a stress diagram of point D, it's like being pulled left to right, being bended, right? Only normal stresses. So this stress diagram is just like a tensile test. So you can so easily draw a Mohr circle like this, and you know the stress is gonna be the value you got earlier. And the maximum shear is going to be half of it. And at the point E, like I said, it's on the neutral plane. There's no stress. So the Mohr circle is like a dot. No stress. So the principal stress and the maximum shear, they're all zero on that particular point. Because there's no stress over there. Okay? So, any questions about the analysis right here? Yeah, go ahead.
How do you know like the V at 250 is equal to 6,000?
How do I know right here?
Yeah.
Because I got the reaction force, only if I got something wrong right here. The reaction force is gonna be 12,000 going up. So earlier I have 1,500 going up right here. And I know the slope of this line because I know how much the distribution load is like this. Every millimeter I have 30 Newton. And I know it's definitely going up because weight goes up. So whenever I move by 1 millimeter, it goes down by 30. Then that's indicating the slope. So I know if I move up to 250, then I can compute for this point. It's gonna be negative 6,000. Okay, then I have another reaction forces at B going up. If my calculation is right here, then it's 12,000. So it's going up 12,000. That's why you got 6,000 here. Okay. So my mistake could only be coming from incorrect balance of moment. So you guys can double check. Maybe I made something wrong here. But if I'm wrong, if I'm right here, then the shear diagram should look like this. I think it would be right because at the end, here we have 1,500 Newton force, and this gives me 0 at the end. So usually the shear diagram goes back to 0, then that's usually that's right. Okay, here is positive 1,500, and going through all these, and then going down 1,500 and reaching 0. So that's then you can tell it's a balance. Okay, so yeah, go ahead.
老师，那个最后一题就是
this one.
对它下面应该会有减 dB 嘛，因为1点会有 IB 分之 dQ 的那个，会有2个
shear force，
它下面应该会折减 IB 分之 dQ。
IB
分之 dQ。 在1点应该会有那个力，应该会有那减。
But there's no torsion.
没有，它不用 torsion 就好，它就是因为 moment 而产生的减力，不是会有吗
Why? It's a neutral plane.
就是2的减应力，如果向下压，它会产生一个分割力。
Let me think about it. It's really? about the normal stress everywhere going down, and then multiplying the radius. So there should be a shear. There should be a shear moment. Okay, so you're saying maybe you're right. So you're saying there's a distributed stress everywhere, and at this point, all the stresses right here will generate some kind of shear going up, down, right? Is that what you mean?
I'm not sure.
Okay. Maybe you're right. If you're right, then the last problem, my answer is wrong. If that's the case, I need to think about how to compute that. Yeah. Because if you are dealing with self-weight, so there's an assumption where I need to assume all the loads are right at the middle, not on the edge. Then there's no force. If I assume all the weight only lies on the central axis, all the weight are right here. If that's the case, then it's like on the side, all the weight are at the middle. If that's the case, if this assumption is right, if all the load stays at the middle, then it doesn't shear the edge, right? Does that make sense? So if I talk about here, there's no force. So my assumption was poor. When I talk about distributed load, in reality, the distribution should look like this. Okay, so you're right. Whatever distributed load on the right-hand side in this cross-section will make some kind of moment. And you can say it's a shearing moment. But my assumption was poor. So I can eliminate that problem, give you some points, because my assumption was not precisely done. But if you truly want to compute this, you need to take integral. It's very troublesome, because it's a distributed load along the cross-section. You need to figure out what would be the shearing profile, and then realize how much shear you have. Then it's troublesome. Then you can figure out what would be the shearing stress right here. It's not a linear. It won't be a linear shear. It's non-linear because it's a distributed load. So yeah. So I think do you agree? Do you think it makes sense? So I think what you're talking about is over here. There is something pulling, right? Is that what you say?
No.
Okay, so then tell me again what you do mean.
就是量它好像是它有一个剪力，就是它有一个向下剪切力的时候，它侧面就会产生一个剪力，就它向下压，因为弯曲而产生一个剪力。让中间就是会产生一个最大，就是两个中立面产生一个最大。
Okay, I need to know what you're talking about. So, if you have a shaft, and if you are starting from the top, and if you only have pure bending, for example, if you bend this way.
就是两个中立面。
Yeah, if you do that, over here you will have compression, right? But from the side, it's a neutral plane, right? So for the neutral plane, there's no normal stress. Are you talking about the shear? You're talking about the shear, right? Okay. So there should be shear on that side. Oh, so the shear would be what we got. So shear would be this, right? So you're saying over here, the shear would be the shear we computed. I'm not sure. I think you're right. Because there's actually shear. So if there's shear, then we need to compute for shear stress. So how do we compute shear stress? That's the problem. So over here, is it really zero force or have some shear? I need to think about it, okay? And also there are issues about what I said right here. There's also issues of these. So it's not a very good problem, to be honest. Okay. Maybe later on we can use ANSYS to prove what would be the normal stress and the shear stress at those positions. Okay. I can just ignore right here. How about this point? Do you agree? Do you agree there? Do you think there's shear as well for this point?
At this point, shear stress is really zero. For the
You think the shear is
for
zero?
the equation I equals dq.
So you think there is no shear right here?
Yeah.
Okay. So now the argument is on this point. We can all think about what's the shear at point E. So it's my bad. I think there is some assumption making the analysis right here confusing. So I will eliminate the points for this particular part. Okay. Well, I like you guys thinking about how the real answer is. I'm okay with arguments, and he could be right. And I know in reality, the distributed load on the edge will definitely pull this way, and of course the distributed load on the left will pull counterclockwise. So it's like on the Z direction is being pulled on both sides. So if it's being pulled on both sides and it's crossing its surface, then it's gonna be shear. So that's definitely, in reality, there's shear. So my assumption was not clearly enough to avoid this kind of confusion. Okay. Okay, so I will go back and make some careful study on what would be the true analysis over there for discussion. And I will make proper correction for the assumption so we can compute in this way. So for those further analysis, I will be just posting those for discussion. Okay? And I won't use it for scoring. And no matter what we do here and there, in real mechanical design, we most of the time need to rely on simulation. We usually study for von Mises stress and then apply to the maximum distortion energy model. Okay, so anyway, are you guys okay? Hello? Hello? Yeah, I know. We can, I mean, are you okay right now? We can discuss further after. Am I over time? Okay. Any other questions? So I think I can only make further discussion of this point after today's lecture, but I will we will figure out how to do makeup. Okay. I haven't decided how we can do makeup or how and when. So we will announce later on. Or maybe we don't release it today. We need to give them some points. Okay. Tomorrow we continue on the maximum distortion energy model. Okay. See you tomorrow.